Hello everyone, thanks for attending our session. Today we are going to show you how we can bypass memory corruption mitigation using speculative execution. Before going into the details of our talk, a little bit about ourselves. My name is Andrea Mambretti and I'm a system security researcher at IBM Research in Zurich. I'm also a PhD student at Northeastern University. Along with me, there is Alexandra Sandulescu. She works at Google and in the security team, and she's a former colleague of us in IBM Research, where this work was actually done. Okay, before going into the details of the technical details of our talk, we need to look at what transient execution is. Transient execution, it's a type of execution that happens in modern CPUs that are highly optimized, and these CPUs, whenever there is a possibility to guess for future operations to optimize the pipeline, they will employ transient execution that will start the execution of a series of transient instructions, and these instructions will cross the pipeline in the backend of the CPU, and their output is actually unknown. So we don't know what is going to be the possible outcome for each one of these instructions until the very end. And the CPU will decide when they reach the end of the pipeline if retiring these instructions, and that means that their side effects will be architecturally visible to our program, or basically squash these instructions. And that means that the CPU has decided that the optimization, the guess that was employed was actually not correct, and these instructions are not needed anymore, and therefore will try to roll back all the side effects that these instructions have left in the backend of the CPU. The problem is that this rolling back of the state of the microarchitecture is not complete, and actually this allows for a possibility for attacks. So an attack in the transient execution works as follows. We have some transient instruction that is generated by the CPU because of some optimization, and this transient instruction will access a secret. The idea here is that by accessing the secret, these instructions will leave some footprint in the microarchitecture that are not rolled back by the CPU when this instruction will be squashed. And an attacker, through one of the many side channels that are available in the microarchitecture, will be able to leak this footprint and will be able to basically find out what was the secret that was accessed. So what is the threat model for this type of attacks? So the threat model is always a victim program that is holding a secret and is handling a secret. And the idea is that this victim program running on a CPU that employs transient execution will leave some side effects behind. And we will have an attacker program running on the same machine that is trying to look at these footprints that is left behind and try to guess what was the secret handled by the victim program. So let's now have a look at one example of speculative execution attacks. Let's have a look at Spectre version 101, which is also known as a speculative buffer overflow that was presented by Kiriansky back in 2018. This attack leverages a piece of code such as this one, where we have a buffer and we have a bounce check on this buffer before making a store towards the buffer. So here is the layout of the stack of this little snippet of code. We have the array, and we have some other information stored in the stack. So when we start to execute this piece of code, when we reach this instruction, as you can see, the size of the array is not present into the cache. We assume that this value is not present in the cache. And we also assume that the x, the value of x, is under attacker control, and it's actually out of bound. The CPU, modern CPU, since the size of array is not ready, will not stall, but it will start to speculative execute. And if we assume that this piece of code was executed many times before with X inbound, the CPU will be tricked to think that X is inbound also this time. And so the CPU will move on to this instruction, and it will perform the store that is out of bound. Basically, we are going to achieve the buffer overflow in a speculative manner. As I said, X is under attacker control, and if you assume that the attacker is powerful enough to know where, for instance, the return value on the stack is stored, the attacker will be able to overwrite the return value. And if you assume that the speculative window is actually long enough to reach this return, the attacker will be able to perform basically a speculative control flow hijack using the value that was overwritten on the stack. At this stage, basically the attacker is able to steer speculative execution wherever he wants, and the idea is that the attacker will want to send the speculative execution towards a piece of code that we call speculative execution side channel send gadget. And this gadget will allow the attacker to leave some footprint that can be read out from another process using a known side channel. This type of attacks is not the only attack that allows us to achieve speculative control flow hijacks. There are many other ways to achieve this very powerful primitive. Let's have a look at the overview on how can we achieve speculative control flow hijacks. So we can achieve speculative control flow hijacks by leveraging microarchitectural components such as the RSB and the BTB. The RSB, the return stack buffer, is used to predict return instructions when the value is not ready on the stack. Or the BTB is used to predict the possible outcome of an indirect call or indirect jump where the target is not known during execution. And these works have proven that this type of attacks actually work. We can poison this internal structure of the CPU and then have a victim use those poison value and basically redirect the victim wherever we want in a speculative control flow hijack manner. On the other side of the spectrum, we can achieve speculative control flow hijacks using architectural components such as registers and memory locations. And we can poison these elements either with a speculative override or a concrete override at the architectural level. And we can overwrite in both of the cases backward and forward edges. So these big family this subfamily of speculative control flow hijacks, we call them SPEAR, speculative architectural control flow hijacks. The first case, the speculative overwrite of a backward edge, was actually already considered by Kiniansky in the speculative buffer overflow. However, the other three cases, nobody has ever looked at them, and we did it in our work. So we tried to find use cases for these three other overrides. And what we did was we started to look at the mitigations, memory corruption mitigations. We started to look at these memory corruption mitigations because, for instance, if we have an architectural overwrite of a backward edge, which is a normal buffer overflow, of course, if there is no mitigation in place, we can perform a buffer overflow, so memory corruption, we can exploit the memory corruption vulnerability, so we don't really need the speculative execution. But in the case of where we have this primitive, but the primitive is mitigated by for instance, a stack smashing protector, then we wanted to investigate if we can leverage speculative execution to bypass such protection and still perform some sort of attack. The first step we did towards analyzing these three cases was actually using a tool that we wrote to observe speculative execution and called Speculator that we published at TACSAC 2019. And with Speculator, what we tried to do was actually to verify if we can perform this control flow hijack. And we wrote for each one of the cases a small snippet of a small test such as this one. This one refers to the architectural overwrite of a backward edge. And this test works as follows. So we first make a copy of the return value that we have on the stack, and we save it in a different memory location. Then we perform the architectural override. We basically simulate a buffer overflow, and we point the new return address towards a target location of our choosing. Then we use a CLFlush instruction to evict the saved return value, so that when we reach this comparison that is going to try to figure out if the value on the stack and the value saved are actually the same, basically the CPU will not be ready to execute this instruction until the stored ret comes back from main memory. And so we trigger speculative execution at this point. Of course, this, at the architectural level, this piece of code will always reach the function myExit, but since we are tricking the CPU to actually start speculative execution at this comparison, we expect the speculative execution to actually reach this return instruction. And if this piece of code reaches the return instruction, then it will use the poison value that we have on the stack. So we will send the execution to our target location. And Speculator is able to see if speculative execution will reach the target location or not. So these are the results of our findings for each one of the tests we wrote in each one of the cases. And as you can see, we have speculative control flow hijacks happening almost 100% of the time. So this type of hijack happens. Of course, this is a lab test. So it's really far from an actual attack, a real-world attack, but it's the first step to understand if these attacks are possible or not. Alexandra now will basically walk you through to actually the real-world attack that we build after we figure out that control flow hijack actually is possible in these cases. We demonstrate a local arbitrary memory read attack using the Spear architectural backward edge overwrite attack vector. The scheme here shows an overview of the steps required to perform the attack. The attack has a preparation phase in steps 1 and 2, where eviction sets are identified. Memory used by the side channel is flushed and rope gadgets are prepared. The attacker then submits the payload to the victim in step 3. The payload is crafted to exploit the stack buffer overflow. Here, traditional exploitation of the memory safety violation is prevented by SSP. However, the attacker uses a speculative execution attack to bypass the mechanism by overwriting the return address and obtaining a speculative control flow hijack. As a result, the victim is tricked into executing a side channel send of attacker-chosen memory location. This happens in step 6. This is achieved with the ROP component, which reuses code snippets from the victim program, which are selected and primed in the initialization phase. The attacker can then execute the corresponding side channel receive in step 7. The success rate of the attack is increased by concurrently executing an eviction loop to lengthen the speculation window with previously computed eviction sets for the stack canary. The Spear attack vector present in an SSP hardened program will provide us with the necessary speculative execution primitive for arbitrary victim memory read. We'll first discuss the vulnerability and the necessary attack building blocks. This code example shows a function which is vulnerable to stack buffer overflow but is protected by SSP. There is a call to memcopy which has like an attacker-controlled source and size, which overwrites the stack past the store return address. The malicious payload will be architecturally written to the stack in this case. The canary check makes the stack buffer overflow vulnerability unexploitable.
in an attempt like this, the program will abort due to the canary mismatch. However, even if SSP protects against the architectural exploitation of this vulnerability, it also provides us with the primitives for a speculative control flow hijack. The canary check executed before the function return will trigger the speculative execution if the instruction operands are not cached. And in order to trigger the speculative execution of the vulnerable path, which is the one taken, the attacker will send a number of valid requests prior to the malicious one. In our experiments, 5 valid requests are enough to train the pattern history table such that the taken branch will be executed speculatively after the canary cache miss. The compiler-generated assembly code for SSP shows the exact operations and control flow graph. In the function prologue, the global canary value is stored on the stack, and before return, the canary integrity is checked by comparing the value stored on the stack with the global value. This introduces the first attack prerequisite, namely the canary eviction. This triggers the speculative execution of the taken branch, leading to speculative control flow hijacking. The next attack prerequisite is a reliable read primitive constructed from rope gadgets that are present in the victim memory space. Even if SSP is supposed to protect against the function ever reaching the return with a corrupted stack, at speculative return, the control flow reaches the attacker-crafted rope chain. In our experimental setup, we tested a rope chain with 5 gadgets and also a stack pivot with 5 gadgets, and we concluded that the buffer override size must be greater or equal to 40 bytes to fit the chain. The victim stack canary eviction will give the attacker a large enough speculation window for the spear attack. The first step of the attack is finding the correct eviction sets for the victim stack canary. We use 2 different processes for the attack that communicate to shared memory. One of the attackers, it is compiled with SSP, is the one on the right. They both run a synchronous loop. The first one will load one LLC eviction set, and the second one will probe the canary access time. And for exactly one eviction set, the attacker program on the right will encounter a cache miss. And as a result, the attacker will know the exact LLC slice and cache set corresponding to the canary of the other process. Now, the next part, the attacker must make sure that the victim canary lies in the same physical memory location as the one discovered previously. We evaluated the reuse of the underlying physical page of the canary in 3 different setups. The first setup is when the victim program is exec by the attacker. In the second setup, the victim is a separate process spawned by the attacker. And in a third setup, the victim is a completely separate process running on the same system as the attacker. The canary page reuse success will be 100% for the first 2 cases due to the body allocator, deallocation, and allocation patterns. But for the latter use case, the success will depend on the resident memory statistics granularity present on the machine that the attack runs on. In this example, we will consider the first scenario where the attacker process will exec the victim program, and thus the canary memory page is preserved at victim startup. The sets that were previously computed are still usable such that the attacker can now evict the canary value in the victim process. To address the canary eviction, we came up with a novel approach of evicting victim data. For existing methods incur high penalty on the ROP execution success. Our method has the advantage of being non-intrusive and noise-free compared to existing solutions. Now, regarding speculative ROP, the attack payload is composed of carefully chosen ROP gadgets that are prepared as part of the initialization phase in step 1. The gadgets must be chosen from code pages that are already present in victim memory and have a valid TLB mapping. Moreover, during ROP chain initialization phase, the attacker executes the chain in a loop pinned to the same physical core as the victim process. This, in our experiments, lowered the chances of instruction cache misses during ROP chain execution. The canary eviction will ensure a long enough speculation window inside of which we run the attack payload. The outcome of this attack is a side channel send represented by an effect on the cache which cannot be rolled back when misprediction is detected. In contrast with traditional ROP, speculative ROP gadgets must be chosen such that the chain has the minimum possible length. In the paper, we show exactly what gadgets worked in our attack and from what libraries and binaries we obtained those gadgets. In this example, however, the gadgets are the basic building blocks of the successful arbitrary victim memory read followed by side channel send. In the first gadget, we see that there is a load of the victim secret byte. This load, to increase the success of the attack, this load should hit the cache. This will provide, during the speculation window, will provide the attacker with the victim secret byte that they intend to leak. The next gadget will compute the exact offset in the side channel array that corresponds to the victim secret byte value. To reduce the noise at the receive end, each side channel array element is of size 256. The noise source here comes from adjacent cache lines being fetched together with the requested line. Next, the side channel array base is added to the previously computed offset, resulting in the memory address of the entry corresponding to the victim secret byte value. And lastly, a load is performed in order to bring this exact side channel array element in cache. This operation represents the side channel send operation. The attack uses the de facto option in speculative execution attacks, namely the cache side channel, although other side channels would work as well here. The cache side channel can use any shared memory region between attacker and victim as side channel array. For example, any dynamic library used by the victim program. The shared space constraints that we found, the attack needs at least 64 kilobytes size and eventually low noise. The attacker may prefer a shared library which is not accessed in close time proximity with the attack. For convenience here, we used libpthread. The side channel array is primed by the attacker immediately after sending the payload by flushing all array elements from all cache levels. Since the memory area is shared between the attacker and victim, the attacker can execute this phase on its side. The attacker triggers the side channel send operation on the victim by crafting a payload that triggers the spear vulnerable code path and eventually hijacks the program control flow during speculation window. In step 7, the attacker will probe the array to read the side channel signal sent by the speculative ROP. In the absence of noise, the probing will result in one single side channel array element cached. This would reveal the victim secret value corresponding to the side channel array element. The end-to-end spear architectural backward edge overwrite attack results in a local arbitrary memory read of the victim memory. We achieved an end-to-end leakage rate of 0.3 bytes per second. To increase the success rate, there is a phase in our attack where the attacker needs to run co-located with the victim, but for a short period of time. Various noise sources require the attack to be executed multiple times in order to distinguish a clear signal during side channel receive. For this reason, we ran the attack 100 times for each victim byte to filter out the noise. And our measurements in here include the victim crash and startup times. The attack works on Skylake and Coffee Lake with all Spectre mitigations enabled. And we also tested on 2 Ubuntu versions, 16.4 and 20.4. We observed a slight success rate change in 20.4 due to another bin utils version. And to increase the attack success and reduce the noise, further work would be needed on the ROP chain optimization side, attacker and victim synchronization, and less noisy side channel arrays. For the next part, mitigations and future work, I'll leave Andrea to continue.
Thank you, Alexandra. At the beginning of the presentation, I was mentioning that we also looked at other use cases, and among these use cases there is the memory safe languages. In this category, we looked at Go and Rust in particular, and we found out that both of these languages, when they introduce security checks, they basically introduce avenues for spear attacks. They both are affected. We wrote POCs for each one of these 2 languages. And for Go, we contacted the Go security team in November 2019, and we discussed with them possible solutions. And the outcome of our discussion was this new Spectre flag that was introduced in Go version 1.15. And so with the use of this flag, basically these problems, the spear problem was resolved. For Rust, we reported our findings in December 2020, and we are currently in discussion towards a solution for this. More details about our work on memory safe languages can be found in our Euro SMP 2021 paper. The final use case that we looked in during our work was actually the control flow integrity case that is related to the architectural overwrite of forward edges. In this case, we looked at the implementation of LLVM CFI and GCC VTV. We found out that LLVM CFI was actually not bypassable using spear attacks, and this is due to one very fortunate design decision from LLVM that basically embeds some of the metadata within the pointer, and so when we try to evict the metadata, we also evict the pointer, and so the speculative execution will block. And also there are other checks that LLVM CFI introduces, but they are against constant that are in line in the code, so we cannot really evict those and to start our attack. For GCC VTV instead, the type of checks that the GCC VTV introduces is actually vulnerable to spear, and we have a small POC that proves it. One key point from our analysis of control flow integrity is really that this type of attacks, the spear attacks, are really implementation dependent. So each one of the mitigations, each one of the versions of the mitigations that are out there should be verified to be resilient against this type of attacks. Again, more details on how we did our analysis on control flow integrity is available in our EuroSMP paper. So so far we didn't really speak much about mitigations. There are of course mitigations against our spear attacks. One set of mitigations is actually instrumentation of the application that we want to protect. There are already compiler passes that helps the user to instrument the application against the spear. For instance, we have the LLVM speculative load hardening. The problem with this type of approach of inlining defenses is that there is always a very fine line between a hard trade-off between coverage and overhead. So the more patterns in the code we protect, the higher is the overhead, and so it's very hard to find which are the sensible code patterns that we want to protect versus the one that we want to leave not protected. Examples of this type of instrumentation, there are fencing instructions that can be inlined in the code, there is branchless masking or constructs such as red Pauline. There are other type of mitigations that the microarchitectural community has been working on, and these mitigations aim to change the design in which the CPU works. And the idea, one line of work is actually to introduce data flow analysis in the CPU pipeline such that the CPU will be able to identify unsafe operations and will be able to block those unsafe operations to take place and delay them when it's safe for them to be executed. This line of work would actually prevent completely all our spear attacks. The second line of work instead focuses on changing the cache hierarchy design such that side channels and cover channels in the cache will be eliminated. While this is effective for certain spear attacks that are based on the cache, they do not work for spear attacks that are mounted with other side channels, for instance, port contention or BTB. One problem with this type of design approach is that they only cover new iterations of the CPU, but they don't cover currently existing architecture. So what are the takeaways of our talk? So we showed that we are able to bypass using a spear current mitigations and memory safety mechanism to leak confidential data. One key point here is that new and old mitigation should be analyzed to see if they are actually resilient against these attacks, and some of the design must change to basically make sure that spear attacks are not possible against them. As Alexandra showed you, these type of attacks in real-world settings have many stages, and they are and each one of these stages has a success rate, and everything should work together to have a successful attack. But it is also shown that they are practical, that we can achieve an end-to-end attack. And the idea here is that with new tools, more tailored tools again, towards like automating each one of the phases, will improve again the practicality of this type of attacks. Finally, in our end-to-end POC, we employ speculative ROP, and we show that it's possible to use speculative ROP in these attacks. And this technique actually helps a great deal to, for instance, build complex gadgets such as the Spectre V1 gadget side channel send that really is hard to find normally in the user's code. In general, we foresee that speculative execution attacks will be the challenge for the next decade. So far, we still lack of many tools to understand and study and build these attacks, as well as like only very few attacks have been studied, and we believe that the attack surface is still quite large to be explored. And also we will need to work a lot in defenses because as I was mentioning before, for instance, in the inlining type of defenses, it's very hard to find the right trade-off. And so we might need to come up with a better heuristic for this. And with this, I conclude. Here are some of the references that we used during our talk. If you have any questions, thank you.